You know that feeling, right? You run a plastic comb through your hair, maybe on a dry day, and then suddenly, like magic, it can pick up little bits of paper.
Hmm.
Or, you take two magnets and you feel that invisible push or pull. It's definitely a force, but there's no actual touching involved.
Right. It seems completely different from obvious contact forces.
Exactly, like when you slam on your bike brakes. You feel the friction, you know it's contact. That makes sense. But the comb, the magnets, that's what scientists used to call action at a distance. It felt a bit spooky, honestly.
It really did, and it remained kind of mysterious until we developed the concept of the field. That's the key idea
The
here.
field, okay.
Yeah, the field is like the framework that explains these non-contact forces.
Hmm.
So the paper isn't reacting directly to the comb itself. It's reacting to the electric field that the charged comb sets up in the space around it.
Ah, I see. So the force is mediated by this field thing.
Precisely. And what's really powerful and kind of beautiful is that this field concept gives us a common language. It works for gravity, for electricity, for magnetism, all these things that act without physical contact.
So understanding one helps with the others.
Absolutely. If you get the hang of how gravitational fields work, you've basically got the blueprint for understanding electric fields too.
Yeah.
Our mission today really is to use gravity as the key to unlock how all these fields behave.
And there's a unifying principle connecting them all.
There is. And it's fundamental. It's the inverse square law.
The inverse square law. Okay, I think most people have bumped into this with light, maybe without realizing the name. Like, if you move double the distance away from a light bulb,
Right.
the brightness doesn't just get cut in half, does it? It drops much faster.
Much faster. It drops to 1/4 of the original intensity.
Yeah.
Double the distance, quarter the intensity, or triple the distance, it drops to 1/9.
And you're saying that exact mathematical relationship governs gravity too?
Exactly the same. The gravitational force, let's call it $5, between two objects is proportional to 1 divided by the square of the distance between them. $5 is proportional to 122 hours.
Okay, let's pause there because, well, that simple rule has a really bizarre consequence, doesn't it? If the force drops off like 122, it never actually hits zero unless R is infinite.
That's absolutely right. The influence of a gravitational field, or an electric field for that matter, stretches out, theoretically, to infinity.
Yeah.
The force only truly becomes zero at an infinite distance away.
Which sounds purely abstract, maybe even irrelevant.
You'd think so, but it's actually crucial for practical things. It's precisely because we know gravity follows this inverse square law so perfectly, fading predictably even at vast distances, that we can calculate, say, the path of a space probe heading to Jupiter with incredible accuracy, or track asteroids that might come near Earth.
That infinite reach is what makes prediction possible.
Exactly. And it took someone like Newton to make that leap.
The famous Apple story.
Well, yeah, the apple story is symbolic, right? But Newton's real genius wasn't just noticing an apple fall. It was realizing that the force pulling the apple down didn't just stop at the top of the tree.
It kept going.
It kept going, stretching all the way up to the moon. He realized the moon is constantly falling towards the Earth due to this same force. It's just that the moon also has a huge sideways velocity, so its fall path curves around the Earth, keeping it in orbit.
So he connected the everyday, the apple, to the cosmic, the moon, using this inverse square idea, universal gravitation.
Precisely. He made gravity universal. But just knowing the force exists isn't enough. To really use this, we need to be able to quantify the field itself at any point in space.
Right. So how do we measure the strength of this invisible field?
We define something called gravitational field strength. We usually use the symbol d out of dollar. Conceptually, you define it as the force experienced per unit of mass. So take a dollar.
Force per unit mass.
Yeah, imagine you place a tiny, tiny test mass at a particular point in space. The field strength of dollars at that point is the gravitational force, $5 acting on that mass, divided by the mass dollar itself.
And why does the test mass need to be tiny?
Ah, good question. It's sort of a theoretical ideal. We imagine it being infinitesimally small so that its own gravity doesn't significantly disturb or change the gravitational field we're trying to measure. You want to measure the field caused by the main source, like a planet, without your measuring device messing things up.
Got it. So $5 is force per mass, measured in newtons per kilogram. But hang on, back in school, it was always acceleration due to gravity, right? Like 9.8 meters per second squared on Earth. How can it be both force per mass and acceleration?
That is a fantastic question, and it touches on something really deep, the equivalence principle. It's the idea, or rather the observed fact, that inertial mass, the m in Fuzzlet, the resist acceleration and gravitational mass, the m in the weight formula, that causes and responds to gravity, are experimentally identical.
They're the same thing, even though one is about resisting pushes and the other is about gravitational attraction.
As far as we can tell, yes. They are fundamentally the same property of matter. And this equivalence has been tested with mind-boggling precision. Experiments have shown they're identical to within one part, and like 10 to 15, that's one part in a quadrillion.
Wow. Okay, that's precise.
Extremely. And because inertial and gravitational mass are equivalent, the units in Cauchy, force per mass, are dimensionally the same as ms_2 acceleration. So ms_2 really is both field strength and the acceleration a free-falling object would experience at that point.
Okay, that clarifies a lot. So Newton's full law of universal gravitation, that brings in the masses of both objects, right?
Yes. The force 50 Corny between two masses, m of $10.6 separated by a distance to sooner, is given by $4 g frac m of 1 liter 2.
And that g is the constant.
That's the universal gravitational constant. Check. It's a fundamental constant of nature. And its value is tiny, something like $6.67 times 1011 in standard units. That small number tells you that gravity is actually an incredibly weak force compared to others, like electromagnetism.
Which is why you need planet-sized masses to get significant gravitational effects, unlike the comb in paper.
Exactly, but notice something really neat here. We define the field strength, dollars, as $5. Let's say the mass creating the field, like the Earth, and $, is our small test mass.
Okay.
So the force on the test mass is 1 g h ump2 barrel. If we then calculate g dollar fm dollar, we just divide that force by dollar.
Ah, so the mass of the test particle, the m, just cancels out.
It cancels out completely. So the gravitational field strength, dollars at a distance, charted from a source mass, is simply g all is simply g mr22.
So the strength of the field at a point in space only depends on the mass that's creating the field and how far away you are. It doesn't depend on what you put there to measure it.
Precisely. Whether you place a feather or a bowling ball at that point, the field strength itself, the property of space at that location, is exactly the same. It's determined by the source, mass dollar.
That's elegant. But getting to that elegant formula was a huge historical struggle, wasn't it? It wasn't just Newton having a sudden insight.
Well, absolutely not. It was built on centuries of observation, debate, and what was probably the biggest shift in scientific thinking ever.
You mean moving away from the idea that the Earth is the center of everything?
Exactly. The shift from the geocentric or Ptolemaic model Earth at the center, everything orbits us, to the heliocentric model, where the Earth is just another planet orbiting the sun.
We usually think of Copernicus kicking that off in 1543, and Galileo, of course, who famously championed it later.
Right, Copernicus laid out the mathematical framework. But the idea wasn't entirely new. Way back, Aristarchus of Samos proposed a sun-centered system in ancient Greece. And importantly, Copernicus himself cited several Islamic astronomers in the centuries before him, people like al-Battani, Thabit ibn Qurra, al-Zarqali, who had already been questioning and refining the old Greek models based on their own observations.
So it was a long process of questioning and refining.
A very long process. But the person who provided the crucial data was Tycho Brahe. He was an incredible observational astronomer, pre-telescope, who cataloged star and planet positions with unprecedented accuracy.
And his data fell into the hands of Kepler.
Johannes Kepler, yes. Kepler was tasked with making sense of Brahe's meticulous measurements, particularly of Mars. And he wasn't starting with the theory of gravity, he was just trying to find mathematical rules that fit the observed movement.
Purely descriptive initially.
Purely descriptive. And that led him to his 3 laws of planetary motion. The first was revolutionary. Planets don't orbit in perfect circles, as everyone had assumed for centuries. They move in ellipses, with the sun at one focus of the ellipse.
That must have been hard to accept after millennia of perfect circles.
Hugely controversial. His second law explained why planets seem to speed up and slow down in their orbits. The line connecting a planet to the sun sweeps out equal areas in equal intervals of time.
Meaning it has to move faster when it's closer to the sun and slower when it's farther away?
Correct. And then the third law, the harmonic law. This is the real mathematical gem. It relates the orbital period of a planet, how long it takes to go around the sun, let's call it $2, to the size of its orbit, specifically the average radius.
And that's the T2 Propto R331. The square of the period is proportional to the cube of the radius.
That's the one, specifically for circular orbits or the semi-major axis for ellipses. Kepler found this relationship purely from the data. He didn't know why it was true.
But Newton did.
This is where Newton connected all the dots. He showed mathematically that the only force law that could produce Kepler's third law, T dollar propto R33, is a force that decreases with the square of the distance and inverse square law force.
How did he show that?
He basically said, look, For a planet in a roughly circular orbit, there must be a centripetal force pulling it inwards, keeping it from flying off in a straight line. That force is related to its speed and orbital radius. He then equated this required centripetal force with his proposed universal gravitational force, DOE MR22. When you work through the math relating orbital speed to period in radius dollars, out pops Kepler's third law, but now with a constant proportionality involving g in the mass of the sun, or Earth, MEL dollars for satellites, T dollars for Kami GME R33.
Wow. So Kepler's observation demanded an inverse square law for gravity. It wasn't just a
It
guess.
essentially proved that the force governing planetary orbits had to be inverse square. It tied the whole solar system together under one mathematical rule.
Okay, we have the math, we have the history, but fields are invisible. How do scientists actually visualize them? How do you draw gravity?
That's where the idea concept. Gravitational field lines do two things. First, the direction of the line at any point tells you the direction of the gravitational force on a mass placed there. For gravity, that's always towards the central mass creating the field. So for a planet, the lines point radially inward.
Straight towards the center, like a plumb line, right? A weight on a string always points straight down.
Exactly. A plumb line is a perfect, simple demonstration of a gravitational field line near the Earth's surface. The second thing the lines show is the field strength. Where the lines are drawn closer together, the field is stronger. Where they spread out, farther apart, the field is weaker.
So near the planet's surface, the lines are dense and parallel, indicating strong, uniform gravity. Farther out, they spread apart, showing the 122 weakening.
Precisely. It gives you a visual map of the invisible force field.
Now, when we draw these lines for, say, the Earth, we usually draw them pointing to the dead center. We're treating the whole Earth as a single point, right? When is that allowed?
That's a great point. We can treat large, extended objects like planets or stars as if all their mass were concentrated at a single point, their center of mass, but only under certain conditions. It works perfectly if the object is spherically symmetrical, meaning its density is uniform, or depends only on the distance from the center.
So a perfect sphere, or maybe layers like an onion.
Exactly. From the outside, the gravitational pull of such an object is identical to the pull of a point mass located at its center. Newton actually spent a lot of effort proving this mathematically. It wasn't obvious.
Okay, center of mass. Is that always the same thing as the center of gravity? I feel like I've heard those terms used interchangeably.
They often are, and in many everyday situations, they're effectively the same place. But technically, they can be different if the gravitational field isn't uniform across the object. Imagine a really, really tall building, like skyscraper height. Gravity is slightly weaker at the top floor than at the ground floor, right? Because the top is farther from the Earth's center.
Following the 122 law?
Right. Now, the center of mass is just the average position of all the mass in the building. It's a geometric balance point, which would likely be near the middle height. But the center of gravity is the point where the total force of gravity effectively acts, since gravity is pulling harder on the lower parts of the building than the upper parts.
The center of gravity would be slightly lower down than the center of mass, pulled towards the stronger gravity?
Exactly. It's usually a tiny difference for most objects on Earth, but it's a real distinction in a non-uniform field. For a uniform sphere in space, though, they coincide perfectly at the geometric center.
That's a neat subtlety. Okay, so we have fields. We can approximate planets as points. This leads us to orbits. And Newton had that famous thought experiment, right? The cannon on the mountaintop.
Newton's cannon. Yes, it's a brilliant conceptual illustration of how orbits work. He imagined a cannon placed on an incredibly high mountain, high above the atmosphere, to ignore air resistance.
Okay.
If you fire the cannonball slowly, it just travels a short distance and falls back to Earth. Fire it faster, it goes further before landing.
Makes sense. Parabolic trajectory.
But Newton reasoned, if you could fire it fast enough horizontally, its downward path due to gravity would curve, but the Earth's surface would also curve away beneath it at the same rate.
So it falls, but the ground falls away just as quickly.
Precisely. The cannonball is continuously falling towards the Earth, but it's moving sideways so fast that it never actually gets any closer. It maintains a constant altitude. It's now in orbit.
It's literally falling around the Earth.
That's exactly what an orbit is.
Yeah.
Continuous falling combined with sufficient horizontal velocity.
It's such a clear picture. But even with this understanding, that original spooky action at a distance problem, it didn't completely go away, did it? Newton himself was apparently bothered by the idea of gravity acting instantaneously across empty space.
He was. He calculated that the effects were essentially instantaneous for the solar system, but he didn't like the philosophical implication of truly instantaneous action. For centuries, it was just assumed the propagation speed was infinite or negligible.
Until Einstein came along.
Until Einstein's general relativity, yes.
Yeah.
GR fundamentally describes gravity not as a force between masses, but as a curvature of space-time caused by mass and energy. And changes in that curvature, like gravitational effects, can only propagate at a finite speed.
The speed of light, presumably.
The speed of light, $2. That was the prediction. And proving it experimentally was a huge challenge.
But we did it recently with the detection of gravitational waves. That was massive news.
Huge news. Starting in 2015 with LEGO detecting waves from merging black holes, that confirmed gravitational waves exist. But the real clincher for the speed of gravity came in 2017.
What happened then?
There was an event involving two neutron stars colliding, about 130 million light years away. Neutron stars are incredibly dense objects.
Okay.
When they collided, they sent out powerful gravitational waves, which LIGO and Virgo detected. But crucially, the collision also produced a burst of electromagnetic radiation gamma rays, which our space telescopes detected.
Ah, so you had two different signals from the same event. Gravity waves and light waves.
Exactly. And despite traveling for 130 million years across the universe, the gravitational wave signal arrived at Earth just 1.7 seconds before the gamma ray signal.
1.7 seconds over 130 million years. That's basically simultaneous.
It's incredibly close. That tiny difference is easily explainable by the complex physics of the merger itself.
Yeah.
The core result was undeniable. Gravitational waves travel at the speed of light. Gravity is not instantaneous.
So, end of the spooky action at a distance mystery, it acts at the universal speed limit.
Pretty much closes the book on that aspect, yes. And modern physics has another layer to this field idea, too, from quantum mechanics. Well, in quantum field theory, forces are understood to be mediated by the exchange of specific particles. For electromagnetism, the exchange particle is the photon.
Right, light particles.
For gravity, the theoretical framework predicts a similar exchange particle, which has been named the graviton.
The graviton. Have we found it?
Not yet. It's hypothetical at this point. Because gravity is so weak, detecting a single graviton is expected to be incredibly difficult, perhaps impossible with current technology. But theories suggest it should exist, and like the photon, it should be massless.
And being massless is why gravity, like light, has an infinite range, consistent with the inverse square law.
Exactly. A massless force carrier particle corresponds to an infinite range force that falls off as 110 tons twirl. So the quantum picture provides a potential mechanism for how the field exerts its influence via particle exchange, even if we haven't seen the particle itself.
So we started this journey with a simple comb, picking up paper, feeling magnets push apart, and we've ended up talking about colliding neutron stars, gravitational waves traveling at light speed, and hypothetical gravitons.
But the amazing thing is that single concept, the field governed by that elegant inverse square law, provides the mathematical language that links it all together, from the smallest scales, conceptually, to the largest cosmic events.
It really is a testament to the unifying power of these physical laws. And the mathematical consistency is key. It's interesting, that Kepler's laws derive for planets under gravity's inverse square pull.
Yeah.
Were later used, at least as an initial conceptual model, by Niels Bohr when he was trying to understand atomic structure, because the electric force holding an electron in orbit around a nucleus also follows the inverse square law. The math had similarities, even if the physics turned out to be much more complex with quantum mechanics.
So the same mathematical pattern appears again.
It does. Which brings us to a final thought, maybe something for you, the listener, to ponder. When Copernicus published his revolutionary book, De Revolutionibus, putting the sun at the center,
his editor, Andreas Osiander, added an anonymous preface, possibly without Copernicus's full knowledge or approval, essentially saying, look, don't worry too much about whether this is really how the universe is structured. Think of it as just a mathematical model, a tool for calculation. What matters is that the calculations match the observations.
So just a useful fiction, perhaps.
That was the implication. It was maybe a way to soften the blow against established religious and philosophical views, but it raises a deep question about science and reality. If you have a model, like the field model governed by the inverse square law, and it becomes so incredibly accurate that it predicts everything from falling apples to gravitational wave arrival times across 130 million light years.
Yeah.
Can there actually be any meaningful difference between a model that is perfectly accurate in all its predictions and calculations and reality itself?
Mm,
If a model works flawlessly, is it still just a model? Or has it, in fact, described reality?
that's a really interesting place to leave it. Is a perfect map the same as the territory? Something to think about.